Welcome to the presentation of the paper, Deep Optimization Prior for Terahertz Model Parameter Estimation. My name is Ming Wong. I am from the University of Siegen, presenting joint work between electrical engineering and computer science as the Center for Sensor Systems, SENS. At the beginning, let us briefly introduce about terahertz imaging. Terahertz radiation is commonly referred to the spectrum between 300 GHz and 3 THz, which is the band between microwaves and infrared radiation. Terahertz imaging systems have great potentials in applications like contact-free material analysis, non-destructive testing, process quality control, and civil security. Among different system designs, frequency modulated continuous wave terahertz systems is one of the most popular ones because of its advantage to allow reconstructing depth information for a three-dimensional spatial object representations. The FMCW terahertz system captures signals by the grid-based movement, as shown in the figure 3, and forms a 3D image with real and imaginary channels. By considering the real and imaginary parts as two separate channels, the terahertz data is represented as a 4D real data tensor, which is the resultant data of a forward model, A, based on model parameters, including the electric field reflectance, the depth positions, and the phase angle. Taking an example shown in figure 4, the terahertz model parameter estimation is an inverse problem which estimates these physical model parameters based on the terahertz forward model by solving the per pixel non-convex optimization problem, which minimizes the loss between model and the data. The deep image prior approach was proposed for linear inverse imaging problems, which use convex optimization problems by reparameterizing the original image as the output of a CNN. In this paper, we propose a deep optimization prior approach, which reparameterizes a pixel-wise non-convex terahertz model parameter estimation problem via a spatially coupled 3D neural network. As illustrated in figure 5, our approach combines the terahertz physical forward model, A, with the network N as a model-based autoencoder. This model-based autoencoder approach enables an unsupervised training method for the very limited number of terahertz training datasets due to its hours-long acquisition time. Now, what is the architecture of this encoder network N? In this paper, we propose to use a modified UNet-like architecture for the neural network. The reason of choosing a fully convolutional network instead of CNN is because of the high memory and computation requirement of fully connected layers, which is critical in terahertz 3D imaging, as we are working with 5 by 446 by 446 pixels, which is 1 million of output neurons as shown in the yellow block, and 182 by 446 by 446 pixels, which is 36.2 millions of input tensors as shown in the green block. This UNet architecture also couples pixels in large lateral regions, which is an important feature in our applications. Unlike classical UNet architectures, this network comprises two major changes. First, we did not double the number of channels in the encoder part, but insert an intermediate bottleneck. Second, the number of skip channels is increased from the common 4 channels to 160 channels. For a better understanding of these changes, please refer to the ablation study in the paper. In the experiment part of this paper, we evaluate the L2 square loss and root mean square errors to the ground truth of terahertz model parameters using both measurement datasets and synthetic datasets. We compared the proposed approach to classical per pixel optimizers LBFGS and ADAM, and our prior work model-based per pixel autoencoder PPAE, using both the good physical-based initialization point and the bad random initialization point. The result shows that the proposed method finds lower energy minima by avoiding undesirable local minima stuck in the gradient descent algorithm, and the estimated terahertz model parameter is more accurate. Notice that in figure 7, while compared to the error bars of per pixel autoencoder, the proposed method robustly estimates model parameters with less outliers. We also compare the model parameters quality by additive white Gaussian noise, AWGN, and additional shot noise. In figure 8, the fourth and last columns are the estimation by the proposed method. By visual comparison to the ground truth as the first column, the result shows that the proposed method improves the quality of the model parameter significantly. To conclude, we propose a deep optimization prior approach with application to terahertz model parameters estimations. Compared to classical optimizers, the proposed approach shows superior ability to robustly find better local optima in the highly non-convex energy landscape, and it enhances the quality of the desired model parameters. Thank you.